me know if you can't hear me in the back. Sure. Okay, maybe this will help a little bit. Okay, great. So what I want to do in this talk is both discuss some recent work that will be presented here at ICCV, but also provide what I see as potentially a little bit of a higher level view of where we might be going potentially as a community in terms of neural network architecting and going along with the theme of this workshop here today. So this is joint work together with Saidi, Alexander, and Heidi. So before 2012, but also after 1990, the computer vision community had largely been working within the paradigm of engineering features such as obviously very well-known SIF and COG features, and then learning the weights of various machine learning models such as SVMs. So between 2012 and roughly around now, this has transitioned to designing new network architectures, starting from, say, AlexNet, going to the VGG networks, ResNet, and so on. And then using those together with all the techniques that we've developed in deep learning to learn the features and the weights, for example, of the classifier that goes along. So potentially, I think that we're starting to see a new shift now, moving from this paradigm to one in which we're generating something that, or engineering something that I'll call the network generator. And then with this idea of the network generator, learning the networks, the features, and the weights together. So I'll say a little bit more specifically, a little bit more formally what a network generator is later, but I just want to convey some intuition about it now. So you can think of a network generator sort of intuitively as a simple function in Python. And it takes some arguments. For example, they might specify the resolution of the input image, the widths of layers in the network, the depth of the network, strides at different layers. And the output of this function will be an instantiation of the network that you can then train or use for inference. And now you can think about enumerating all possible valid input arguments within some reasonable range. And that's going to generate a population of related networks that all originate from this function class, this network generator. And I think that this is a very natural progression for how to look at how networks have been developed over the last several years within the community. So I want to start by looking at how things were done back around the time of AlexNet and transitioning to VGG networks. So back in that time frame, people were mostly looking at what we can call point estimates. And I'm borrowing these figures and terminology from a paper, also from a group, but that I was a part of, that will be presented here called On Network Design Spaces for Visual Recognition. And so the idea back then with point estimates is that you would build some network, and then you would change arbitrary things about it with no controls, and you would arrive at another model that maybe has a lower error on ImageNet. And you would continue to do this, and it wasn't exactly clear how these networks related to each other or why one was performing better than the other. So then the natural progression of this was to start to add a little bit more control to this experimental paradigm and to look at what's termed in this paper as curve estimates. So the idea in curve estimate is now, rather than having a single network, you will have a small set of networks that are related to each other. So for example, the VGG 13, 16, and 19 networks all sort of follow this modularized design and repeated 3x3 combinations, or ResNet 50 and ResNet 101 networks. And from these few networks, you can start to look at things like a trade-off between the error and the complexity, for example, measured in floating point operations. And people started to quickly realize that there were relationships between these things, and that often simply by increasing the flops of a network, you could decrease the error. So perhaps it didn't make sense to claim that one network was better than another due to some design decision, when actually perhaps it's just better because you've increased the amount of computation that it performs. So then the next natural step in this progression, and which is described in more detail in this paper, is to look at what are termed distribution estimates. So here you have what's called the design space in that paper, what I'm referring to as a network generator, which is capable of producing a family of related networks. And you can, for example, randomly sample networks from this generator and train and evaluate each one. And if you do that, and then you plot a curve, which basically is showing what's the cumulative distribution versus the error of the network, you can start to see for randomly sampled members of this population, what does this trade-off between error look like between different underlying network generators. And in order to have this comparison make more sense, you probably want to do something like only sample networks that are constrained to be within a certain flops budget of each other. So this allows you to vary a whole bunch of different parameters all at once. So for example, the depth, the width, you can arrive at all these different trade-offs between these arguments to it within this constrained flops budget. And you can then see if one critical design factor between these two network generators is actually contributing to one having a lower error across this whole space of randomly sampled networks. So in this comparison here, it's showing the difference between a generator for ResNet versus a generator for ResNext, where the difference essentially is in whether you're using grouped convolution or not in the bottleneck of the network. And you can see that as you vary all of these other parameters of the network, the curve for ResNext is pretty much always at a lower error, which indicates that even if you change a whole lot of other factors, ResNext networks are typically always going to perform better than ResNet networks. So I think one of the reasons why this shift in perspective, going from point estimates to curve estimates to looking at populations of generated networks is important, is because it gives us a little bit more insight into perhaps discovering some more general principles in terms of network architecture design. So from the ResNext example, we can see that group convolution, or in its extreme form of depth-wise convolution, seems to be generally a pretty good primitive for building neural networks. So another example of why this sort of perspective is useful and interesting is that it also allows you to gain some more insight into how the landscape of related models perform with respect to, for example, neural architecture search. So if you look at a progression of NAS-related papers, starting in the NASnet, going through DARTS and ENAS and ENAS, et cetera, one of the sort of subtle things in these papers that might be difficult to pick up on is that the actual design space, or the network generator behind these systems, is actually also subtly changing. So there are kind of two things changing. The one that's typically highlighted in the papers is the optimization of the search algorithm, but also the space that is being searched is changing. And so you might wonder, if I was to remove the search of the optimization part of it and just look at what's the effect of changing the network design space, what impact does that have? And you can use these population comparison curves, these distribution estimates, to see that if you were to, for example, fix the flops and then go through the small changes that are being made to different design spaces, you can see that just by randomly sampling models, almost all of those models are systematically improving as these design spaces are being refined from paper to paper. And so this is an insight that's difficult to achieve without taking this population level perspective. And this also helps to provide some insight into some more recent work that showed that random search is actually a really strong baseline in NAS. And the intuition here, which you can get directly from these distributional comparisons, is that most of these models, except for if you go to this very small portion of the population up here, actually all perform pretty well. So these curves are typically, in this figure, are generated by, I think, 100 randomly sampled models. And so you can get a pretty good model, which for representative down here, just by randomly sampling. And for example, if the design space looked quite different, and if these curves were shifted much more so that a large fraction of the population achieved quite bad performance, then perhaps random search wouldn't be working quite as well. So the last part of why I think this shift in perspective is important is because it allows us to also have a new tool for exploring some scientific questions that might be interesting. So one question that I'll pose and spend most of the rest of the talk on is how does random wiring compare to engineered wiring? So I think that there are a few different perspectives on why this might be interesting and what motivation we might have for looking at this. So the first is a historical motivation. And actually, a lot of the initial work in machine learning and artificial intelligence going back to Turing actually focused quite a lot on this idea of randomly wired networks. In neuroscience, which I won't talk about too much because I have a background in neuroscience and therefore I really want to represent the work. But from what I do understand is that a very popular topic of research is trying to understand what is the random connectivity in the brain and what sort of properties do the graphs out of form actually represent. And so, for example, there are some studies trying to understand whether there are various properties of these graphs, such as being related to small world networks. And then there's a practical motivation, which is that we've seen that a lot of the advances that have happened over the last several years in terms of developing better and better networks have resulted from changes in how these networks are wired. So, for example, a lot of the networks starting from LaNet and going to AlexNet and BGGNet follow this chain-like wiring pattern in which there's basically a linear progression of stages that just follows one path through the network. But then a lot of the more recent networks that have tended to both increase the efficiency of the network but also increase the accuracy of networks, it introduced these multi-path connections in which there are many different ways in which the data can flow. And this also includes how easy it is to optimize deep networks. So this gives some motivation that the wiring of networks is actually really important to their ability to work well in practice. So I also want to relate this to some prior work. So what we'll be looking at here is what I'll term macro wiring. So macro wiring is sort of looking at the way that op-level units like a convolutional operator are connected to each other. There's also another level of granularity which we could call micro wiring, which I think has seen more work in the past. And that's usually looking within an operator such as convolution to see the consequences of the ways in which you can change the wiring patterns there. And so as an example of that, we can highlight this paper from the last ICCV on deep expander networks, which showed a way to create these efficient approximations for fully connected convolutional wirings, but end up being more efficient. There's also prior work that focuses on learning wiring. And so, for example, there's the Mass Connect paper, where the goal is to jointly optimize the weights of the network, but also the connectivity pattern. And the perspective that I'll be showing in the rest of the talk is less about learning of the wiring, but more kind of presenting if you had a baseline for how does a random wiring pattern work, what does that actually look like? Does it perform miserably poorly, or does it actually work pretty well? And how does that compare to learned alternatives or hand design alternatives? And then, of course, there's work in the NAS literature, which jointly is searching for good combinations of operations and sort of macro-level wiring pattern. All right, so now let's go into a little bit more detail in terms of what this concept of a network generator is, since this will be the basis of the rest of the talk. So you can think of a network generator as some function G that's going to map from some parameter space theta to a space of network architectures N. And this parameter theta is basically going to be specific to what you want this network generator to construct. And it's going to contain things that specify, for example, the number of stages in the network, the number of blocks per stage, the depth, the width, the filter sizes, etc. So that describes a deterministic network generator. But you can extend this to stochastic network generators simply by adding another argument, which is the seed of a pseudo-random number generator that's contained within the function G. And so then, if you were to enumerate different values for this random seed, then the same generator function G with the same set of parameters can possibly give rise to a diverse set of different randomly generated models. And so the key idea behind the network generator is that it's a way to sort of more formally encapsulate the entire network generation process. And when you do this, and you actually write down all the steps of the way that the network generator is doing, you start to see all of these sort of assumptions that you've built into the model. So you start to see various empirical priors that you've added to it, which are basically based on our knowledge of what's worked well over the last few years. You see what exactly are the learnable parameters of it, where is randomization being used, and you also start to reveal a whole lot of heuristic rules that perhaps you weren't thinking about as first-class citizens in the network generation process. So going back to NASA as a running example here, we can recast a popular form of NASA that uses an LSTM controller to generate networks within this framework of the network generator. So the LSTM itself has some parameters that need to be learned as part of the optimization of the NASA process. And these parameters are going to control how the LSTM is used to sample actions. So the actions are going to be things like insert a convolutional operator or connect two nodes to each other. And by varying the random seed, this LSTM will allow you to generate different networks. But then, in addition to that, there are all of these rules that have to be brought in, which I referred to before as this sort of miscellaneous heuristic rules. And these are things such as what's the input degree to one of these basic cells that's being generated by the LSTM? Or what's the rule for how you specify how to assign an operator to a node in the network? Okay, so with this in mind, now I want to move on to describing network generators for random acquired networks. So we're going to be designing networks that have these like very crazy looking designs compared to most of the networks that have been created before. Okay, so how are we going to create these? So we're going to start by generating a general undirected graph P, and then we're going to map that graph to a valid neural network. And again, when we do that, there are all these miscellaneous heuristic rules that are going to come into play in that mapping operation. All right, so let's start with the first step. So here we can draw on a whole bunch of different random graph models that have been introduced in the past. So we'll take these three as examples. So there's the Erdős-Renyi model, which is the classic random graph model, in which you're just, according to some probability P, randomly connecting two nodes in the network. There's the Bargasi-Alberg model, BA, which is a model for generating networks with the so-called scale-through property. And then there's the Watt-Strogatz model, WS, which is a model that generates graphs that have a small world property. And the small world property, sort of at an intuitive level, is something that you might have heard of as sort of the 6 degrees of separation, or how many hops does it take to connect you to Kevin Bacon. And each one of these models has one or two hyperparameters to it, which essentially controls the type of graphs that it's going to generate. So here's an example of the Watt-Strogatz model. And so it starts with a regular ring lattice graph, and then according to some probability P, as you walk around the graph, you're going to randomly rewire the node to the environment graph. And if P is 0, then you end up with a deterministic graph. There's only one possibility. And as you increase P, sort of the randomness of the connections ends up increasing. So this gives us three options for a model to generate a random undirected graph. Now we need to go through a number of transformations in order to convert that into something that we can actually use as a computational model from a neural network. So the first step is to convert that into a DAG, or a directed acyclic graph, that's suitable for computation. So in order to do this, you need to use some way to assign an ordering to the nodes in the graph. Again, in the paper we have the details for how we do this for each one of the network generators. But taking the Watt-Strogatz model as an example, you basically just pick a point on the ring lattice and start numbering the nodes going around, and that's how we determine the order for the DAG. And there's no particular reason for doing it that way other than sort of the most obvious way. Now, when you generate one of these graphs, there may be several sort of independent unconnected inputs and several independent unconnected outputs. But we want to eventually form a network that has sort of a classic multi-stage structure that most of the neural networks that have been designed before have. So we need to add an extra input and an extra output node that enable us to create this form. And then we need to define some rules which actually say, how do you take one of these DAGs, which so far has no meaning in terms of the computation it's going to perform, and map that to something that has the semantics of the neural network. And so there are a whole bunch of different ways to do this, but there's a particular choice that we've made here, which I'll say in a moment why we think it's a good choice. So it's quite simple. So the edges are just going to represent data flow. So you can think of them as the node is going to emit a tensor, and that's going to sort of flow along the edge to the next node. And the nodes themselves are going to implement a simple transformation of the data that's going to be based on taking a weighted sum of the inputs that are coming to it, and then performing convolution batch norming. And then if it has multiple outputs, it will just send an output copy of the output along each one of the outgoing edges. And then once that mapping has been defined, we can now assemble a whole bunch of these randomly generated graphs into a multi-stage architecture in which at the end of each stage, we're going to double the number of channels and half the spatial resolution in each dimension. And so these are sort of the heuristic rules that have been developed in between in terms of what are the operations that the node should be performing, and how do we assemble all of these networks into different stages. And by putting all of these under the umbrella of the network generator, we sort of get to very explicitly look at, to what degree is randomness playing in here, and what degree are all of these sort of design principles that the community has discovered playing in this. So going back to this specific choice of mapping edges to data flow and nodes to computation, the idea here is that because we're going to be exploring networks that have a whole bunch of different wiring patterns, and because we know that flops, floating point operations, are related to the accuracy of networks, we want to have a mapping that's going to roughly preserve the flops of the network if we fix the number of nodes, but then allow the wiring pattern to vary greatly. And so by having the wires of the network essentially only define data flow, this allows you to have a greatly varying number of different connectivity patterns that don't really change the underlying flops of the model. Okay, so with this in mind, then you can kind of go crazy. You can generate all of this weird zoo of these different wiring patterns. Some of them, depending on the hyperparameters that are used for the network generator, will end up having deterministic structures, but most of them will have some sort of randomness to them. And so for each one of these settings of hyperparameters, so for example, watch stroke x 4, 0.75, you can sample multiple models from this, which all follow the distribution created by this particular setting of the network generator that have different wiring patterns. Okay, so now let's take a look at how this compares. So we'll look at MobileNet v1 as a reference point for hand-designed network architectures. And all the models here are going to have roughly, not exactly, but roughly the same number of flops, somewhere around 580 million. Okay, so first we'll look at models generated by WS using p=0, which is the sort of deterministic setting. So you can see that some of these models to the standard deviation that you get for this deterministic case. And so here the only variation that you're seeing is due to random initialization of the network in terms of the network weights, not the structure of it. So sometimes the observed standard deviations are quite a bit greater than that, but they're often somewhere kind of in a similar range, which is really showing that within this random family, there's not a whole lot of variation in terms of the performance of the networks that you arrive at. And then we can move over to the BA model, and we can also observe over here that there's sort of a similar trend that for quite a few of the settings of this model is able to achieve quite good performance, and for the worst performing one, it's somewhere along the MobileNet v1 baseline. And then likewise for the erg-shredding model. Okay, so now we can look at this in the context of the performance for other models that have been proposed within the similar flops regime. So this first bracket of results is for various hand design models that have been proposed. So MobileNet, MobileNet v2, ShuffleNet v2. And then the second bracket is for models that have been designed by neural architecture search algorithms. And what we can see is that if we take the best settings, so that was the one that I was using as an example a couple times ago, the Watch-Strogatz 0.75 model, we can see that this actually attains fairly competitive performance with both the hand-designed and NAS networks, which we found this quite surprising. We're not really expecting to see this kind of result at all. So beyond this sort of small flops regime setting, we can also scale up these networks and look at how they perform if we go to, say, the ResNet 50 flops regime. So here, ResNet 50 is sort of the hand-designed wired baseline, and it gets somewhere around 77% accuracy. And then if we look at that same WS4 0.75 generator, and here's a depiction of 3 different networks that were generated by it, they all achieve somewhere right around 79% accuracy. And I think this is quite interesting because when ResNet was introduced, it was sort of a breakthrough of the design that you were able to have these skip connections, and that was really sort of the power idea. In these randomly wired networks, we don't hand code the concept of a residual connection and residual learning. But it should be fairly intuitive that due to the way that these are wired, that you're going to end up with a lot of very short paths from the input to the output. And so it's able to have a similar property, even though that wasn't part of the original thinking or design of it. So I'd like to offer a few conclusions from the perspectives and the study that I presented here. So one is that perhaps as a community we're starting to move from designing individual architectures or very small families, let's say like 3 or 4 related architectures, to designing these meta-level network generators that you can then use to generate populations of networks and use techniques such as neural architecture search in order to find specific models that perform very well. The second point is that I think that there's a lot of power in looking at populations of networks rather than individual networks or curve estimates generated by a few networks. This allows you to see whether there are specific design decisions that would systematically improve the network, even if you're varying a whole lot of other factors. And then one that I think is quite good to keep in mind is that when we're building these networks, even if we're doing neural architecture search or we're using some degree of randomness in them, there's a huge amount of knowledge that's been distilled in the community over time. And a lot of that comes in as a prior that's used effectively to make these networks perform a lot better than they otherwise would if we were really letting things be more random and less controlled. And I think it's important to keep this in mind because it may be a limitation of the approaches that we're using for searching for new networks because they're often quite constrained to actually be very close to things that we already know that work well. And it really would be much more interesting and exciting if we could try to loosen some of those constraints and really find some crazy new designs that work quite well. And then along those lines, one of the goals that I have in mind for the randomly wired network work at the start was I was really hoping that we would be able to discover some sort of properties of the graphs that are behind networks that work well that would allow us to predict whether some new wired pattern in the future will work well. And unfortunately, this hasn't come to fruition yet, but it's still sort of an ongoing hope out there, is that these networks work surprisingly well, and hopefully we can find something underlying in the actual graphs that are behind them that will help us better understand why they're working well. So with that, I'd like to thank you, and that's
Okay, do we have many questions?
Hello. I do know that connectivity is very important, but how do you handle the operations? I mean, just in order to purely study connectivity stuff?
Yeah, so I'll show one of the slides that I left out of this. So we also vary the operations that are being used. So for example, what this graph here is showing is if you fix a set of network architectures, so essentially you can think of this axis here as model index 1, model index 2, and so on. And then if you vary the design of the node operation that's being used, so the dots up here are 3x3 separable convolution, and then the ones down here are either going to be 3x3 convolution or maximally followed by 1x1 convolution, and so on. What you see is that no matter what you choose in terms of the node operation that's being performed out of the set of 4 choices, you end up with a pretty consistent correlation between how the individual networks perform, which is indicating that the role of the wiring seems to be dominant over the actual operations that are being performed by these, at least within this set of
So the question is that we know that many networks work very well because of the prior knowledge. For instance, COMNET work really well on images. So now, if we want to use this NAS to solve problems where we don't know how to put this prior knowledge into the network. For instance, we are going into a field where we don't have a specific network. So can we put this prior knowledge into the network using this kind of formulation to solve a very different problem?
Yeah, so absolutely yes, and actually I think that maybe the critique of network architecture search approaches right now is that we actually don't know how to do the opposite of what you're suggesting. The only thing we know how to do really is take our guess at what will work well, or our prior knowledge about what works well, or some theoretical understanding about the fact that convolutions are well suited for natural images, and put that into the search space. And then within that constrained search space and within those priors that we've built, find something that is a good combination of those. What would be really exciting is if we could go beyond that and have the search procedure find something brand new that we didn't know about before. But I think that's far beyond where we are today.
Aren't there any evidence around this? Is there any research around this?
Well, I think that there's quite a lot of research around it in terms of trying to find. So for example, you might want to define new types of convolution that are invariant to other types of transformations, and there are attempts to do that in order to be more sample efficient in different domains.
So one thing that your talk did not touch upon is the training process for these networks. So is it that you're really finding some architectures being better than the others, or is it that you're just finding that some architectures are easier to train for a given training procedure? So because these two are not decoupled, the architecture and the training process itself.
Yeah, I'm not sure that you really can decouple them. So for example, if you take ResNet as a case, like the architectural change is fundamentally changing the optimization problem, making it a lot easier to optimize. So can you decouple that from the architectural design, or maybe I didn't quite understand.
So for all of these networks, you use the same training, learning rates and schedules and all that, right? So under a fixed learning rate schedule and learning rate process, you found some architectures are better than the other. So is it really the connectivity that is one is better than the other, or is it because you're not using the right training process for it?
Yeah, I mean that's a good question. That's always a concern when there are so many different things that you can do, and perhaps you did exhaustively grid search for various hyperparameters for every setting. So there's always a possibility that if you you did a more exhaustive grid search for some specific point in the space that maybe you derive out of a different conclusion. I kind of doubt that that's likely the case from what we've seen looking at the population experiments in the literature.
So from my experience, if you take a very old ResNext and just use the latest training procedures, let's say for a MobileNet V2 or something, all the results just go up significantly.
Yeah, that's.
So is it really the architecture or is it really the training process that's driving all this improvement?
Well, it's both, because if, for example, you were to take a VGG net and apply the same training process, or a network without batch normalization and apply the same training process, you won't see that they suddenly perform equivalently. So it's a combination of the two, for sure.
Thank you.